Water exists in three phases. We've got the solid phase, ice, the liquid phase, water, and gas, that's our water vapor, okay? And so there is, for whatever element we're thinking about or whatever substance, there are three phases for that substance. You've got a solid phase, a liquid phase, and a gas phase. There is energy associated with changing the phase of a substance, okay? So you either have to add energy to the substance to change its phase or remove energy from the substance to change its phase. So the energy, which I'm going to refer to as Q here, the energy associated with changing the phase of a substance is equal to the mass of that substance times what we call the latent heat. Okay. The latent heat could either be the latent heat of fusion or the latent heat of vaporization. So the latent heat of fusion comes around during melting or freezing of a substance. The latent heat of vaporization comes around during boiling or condensing of a substance. Okay. And so why the plus or minus here? So the plus means that energy is absorbed by that material. So for example, when we melt ice, when we change it from a solid to a liquid, that ice absorbs energy in order to change phase, okay? And negative here is when we have a phase change where energy is removed from the system. So an example of that is when we take steam in the gas phase and we change it to a liquid. So when steam condenses to a liquid, you have to remove energy from the system, and that's when you would use a minus sign. Now, for the labs that we're doing this week, we are only going to be worrying about the plus sign here. We're going to be melting ice. So we are going to be, that ice is going to be absorbing energy to change its phase from a solid to a liquid. So here's the question. How much energy is required to melt a 60-gram block of ice? So how much energy is required to melt? All right, so we're just going to use this equation right here. The energy required to change our ice from its solid phase to its liquid phase. We're going to assume that the ice is already at 0 degrees Celsius. So it's already at just the right temperature to start to melt, okay? So then the energy required to melt this block of ice is just going to be equal to the mass of that ice cube, which is 60 grams, times the latent heat of fusion for water. And the latent heat of fusion for water is equal to 80 calories per gram. Okay, so a calorie is also a unit of energy. So the latent heat of fusion is energy per mass required to change phase. So we're going to take Q equals to our mass times our latent heat of fusion. So the energy required to melt our piece of ice is just going to be 60 grams times the latent heat of fusion, which is 80 calories per gram, and then that's going to equal to 4,800 calories required to melt our piece of ice, okay, or just to change the phase of that piece of ice. And so the latent heat of fusion here, I was using it in calories per gram, but you could also use it, the latent heat of fusion for water is also 3.33 times 10 to the 5 joules per kilogram if you're going to be using it in units where we have a mass in grams and you want to think about energy in joules instead of energy in calories. So usually when we're using smaller masses, it's a little bit easier to use our latent heat of fusion as calories per gram. But if we're using bigger masses, maybe you wanted to use your latent heat of fusion with the units of joules per kilogram. Okay, so over here we were just thinking about what is energy required to change phase. We're not changing the temperature, we're just changing phase of the ice. So we're going from ice of 0 degrees Celsius to water of 0 degrees Celsius. We're just changing the phase. There's no change in temperature. But what happens if you heat up a material to some temperature, Okay, so the heat required to increase the temperature of a mass by some amount, delta T, is this equation right here. So the heat required to increase the temperature of a mass by some change in temperature is equal to this equation right here, okay? So Q is equal to our mass times this C here is what we call the specific heat. It's a property of every substance, just like the latent heat here is a property of every substance. The specific heat is a property of every substance that goes into this calculation. So the specific heat of water, which we represent by this letter C, is equal to 4,186 joules per kilogram degrees Celsius, okay? But we can also write that as 1 calorie per gram degree Celsius. Okay, so let's say how much heat is required to raise a cup filled with 200 grams of water from a temperature of 5 degrees Celsius to a temperature of 25 degrees Celsius. So how much heat is required to raise a cup filled with 200 grams of water from 5 degrees Celsius to 25 degrees Celsius? So to find the heat required to increase the temperature of that water, we're just going to use this equation. Q is equal to the mass of the water, 200 grams, times the specific heat. And we'll just use the specific heat, that's calories, grams, degrees Celsius. So we'll use 1 calorie over gram degrees Celsius. It's nice that it's just 1 when we're using these units of calorie, gram, degree Celsius. And then we have to multiply that by the change in temperature of that object or that substance. So the change in temperature would be our final temperature, which is the temperature we increase it to, 25 degrees Celsius, minus our initial temperature where we started from, 5 degrees Celsius. So 25 minus 5 is 20. So the heat required to increase this temperature of this cup of water is going to be 200 times 20, and that's going to give us 4,000 calories. So our unit of energy here is in calories, because we see that the gram cancels with this gram on the bottom for our specific heat, and these temperatures in Celsius are going to cancel with this temperature in Celsius on the bottom of the unit for our specific heat, and then we're just left with units of calories.